So I will talk about exploring Earth's interior and imaging Earth's interior with 3D wave simulations and the Adjoint method. The Adjoint method is a useful technique to incorporate 3D wave simulations in seismic tomography in full waveform inversions. So in seismology, our goal is to illuminate Earth's interior in terms of seismic parameters such as seismic wave speeds, density, anisotropy, and elasticity, or to determine source parameters such as seismic moment tensor, location, the depth, or the source time function, origin times of the earthquakes, based on by minimizing the difference between the field observed data, which is the seismograms in our case, or some secondary observables made on waveforms, and the synthetic data, simulated synthetic seismograms through an optimization technique, which is known as the inverse problem. And this procedure involves the forward problem, which is the computation of these seismograms, which also directly controls the success and the accuracy of the seismic tomographic procedure. So this is a cartoon image of Earth's interior. So in seismic tomography, our goal is to detect some patterns in the mantle and ultimately in the core, which can be subducted slabs or upwelling mantle plumes, which directly control mantle dynamics, mantle convection currents, and also the inner core and the outer core structure, which are responsible for the generation of Earth's magnetic field. So with the advances in computational power and the increase in the amount of high-quality seismic data, we are now able to use full waveform inversion routinely in earthquake seismology. And after the successful applications at the regional and continental scale earthquake seismology, the most recent global mantle models based on adjoint tomography also came out, in which the core, inner core, and the outer core is fixed to a 1D reference model just because of the period content or the minimum resolution of the simulations. Only the mantle and the crustal structure have been simultaneously inverted. But now, of course, the ultimate goal is to perform whole Earth full waveform inversions, including the core. But meanwhile, of course, that requires going down to 1 second and routinely simulating seismic wave propagation with accuracy down to 1 second at the global scale, which is the subject of exascale computing. But meanwhile, going down to 9 seconds, we can do it successfully, already gives us a great opportunity to start investigating the outermost part of the outer core, considering the dominant period of SmKS phases, which nicely sample our target region, which is the subject of our NSF proposal. So within this lecture, I'm going to make a brief introduction to the commonly used numerical methods in seismology and talk about the adjoint waveform inversions. And ultimately, I will talk about our plans to explore Earth's outer core using 3D wave simulations. And before that, I will give a brief background information about classical seismic tomography. So in classical global seismic tomography, and the global scale imaging will be, and the global seismology will be the focus of this lecture. The goal is starting from a radially symmetric Earth model, such as PRAM, to determine the lateral variations in the mantle and ultimately in the core as well. And this process is traditionally based on ray theory. And because the resolution of the tomographic images we have achieved, finite frequency effects have become important, so they have been incorporated in seismic tomography, typically with respect to 1D reference models. And the usable amount of data is directly subject to the chosen forward theory. So to improve the data coverage, it's common to combine different data sets using major seismic waves And the crustal corrections are commonly used in mantle tomography. And to illuminate the inner core and the outer core structure, mantle corrections are also commonly used. Here is a brief description of ray theory versus finite frequency theory. Here on the top left, you see a phase velocity map of Rayleigh waves at a period of about 150 seconds. So this is an example from surface waves, but the same also applies for body waves. So if we have a source and receiver, we can compute the phase shift along a ray path making the great circle approximation. And the phase shift along the ray path between the source and receiver can be computed by summing up the perturbations in wave speeds normalized by the reference phase speed, integrating along the ray path or the great circle. So in the exact ray theory, we compute the exact ray paths using the Fermat's principle. And then in this case, the phase speed perturbations along the exact ray path are integrated. And however, ray theory is a high frequency approximation where its validity depends on the frequency of waves, propagation distance of waves, and the smoothness of heterogeneities. In short, whenever the scale length of heterogeneities become comparable to the wavelength of seismic waves, ray theory breaks down, where the finite frequency effects become prominent. And in the finite frequency theory, the first order scattering is taken into account within a Fresnel zone, which is described by a kernel here, and integrated over a volume. And this is how the phase shift along a ray path is computed. And this is a better, in theory, this is a better theory than the ray theory, as it incorporates the first order scattering. And in seismic tomography, as I said, it's common to combine different data sets, which can be body wave travel times, minor and major arc surface wave phase and group wave speeds, or normal mode splitting functions, or the waveforms of some specific phases such as S waves or the surface waves. And if the amplitudes can be properly incorporated in seismic tomography, they provide excellent constraints not only for the inelastic structure of the Earth's interior, but also to better locate the elastic heterogeneities. So that's why using waveforms ultimately provides much more information for seismic tomography, and where this is the ultimate goal, to use every wiggle in seismograms. However, in the global classical seismic tomography has some challenges, especially at the stage we are, or at the current resolution we have in our seismic tomographic models. So that's why it is desirable to try to avoid approximations and corrections as much as possible. So the first approximation is the ray theory. So we need to take into account finite frequency effects in seismic imaging. So here you see an illustration of the sensitivity of P waves between a source and the receiver. So where the ray theory tells us that the seismic waves propagate along a ray path here, whereas the finite frequency effects, because we are working with the band-limited data, tells us that seismic waves counterintuitively are not sensitive to the structure along the ray path, but the structure around the ray path within defined by a Fresnel zone. And if you compute these kernels like these data sensitivities in 3D and take a cross-section from the source and the receiver, you have such a banana shape. And if you take an orthogonal cross-section, then you see a hole inside which looks like a donut. And this is how these kernels for body waves have been named as banana donut kernels. But to make the entire story complete, we have to compute the synthetic seismograms and these data sensitivity kernels, which are also known as Fresnel kernels. They have to be calculated numerically in realistic 3D background models. And the data coverage has been one of the major shortcomings in global seismic tomography because of the distribution of earthquakes, which generally happen at the plate boundaries, and the distribution of seismic stations, which generally where we have most of the stations in the continents and in the northern hemisphere. And nowadays we have beautiful dense seismic arrays such as US array, and also in Europe, Japan, China, which provides us great opportunities to image the lithospheric structure and upper mantle structure underneath continents, but they also impose some challenges at the global scale. And of course, the ultimate goal is to cover the entire oceans with ocean bottom seismometers. But in the meantime, we can use some emerging data from new instruments such as floating acoustic robots, mermaids, or also recently popular fiber optic cables are providing great opportunities, potentially also for the oceanic regions by making use of ultimately the underwater cables to better sample the oceans. But meanwhile, we cannot change this distribution, but we can try to extract as much information as possible from our seismic waveforms by making use of 3D wave simulations. So here you see a seismic record section for a deep earthquake in Argentina. And the black seismograms are the observed field data, and the red ones are the synthetic seismograms computed using a 3D crustal and mantle model. And the numbers on the left, you see, they denote the epicentral distance between the source and the receivers, and these are the station codes on the right. So what we observe is that, and also the major phases, body wave arrivals are labeled on the figure, and the seismograms are filtered between 17 to 60 seconds. So what we see, observe is that actually the current mantle models and the crustal models, they are pretty good at explaining body waves. However, when we are running into the surface wave regime and look at the scattered waves, there is quite some discrepancy. And I would like to mention that this is a deep event. That's why the data quality is pretty good because the crustal effects are less. Not all the seismic records are so clean, but still it's a good illustration. So this discrepancy between the observed and synthetic data is not a problem for us because this is where our job starts. Basically, our goal is now to minimize this difference between the observed and synthetic waveforms iteratively using the adjoint techniques. So another challenge is that crust can be highly nonlinear, which makes the commonly used crustal corrections questionable. So in classical seismic tomography, array-based seismic tomography, it's pretty challenging to try to invert for crust. The very thin but highly heterogeneous crust has a strong influence on seismic waveforms, specifically on surface waves. However, it's also pretty challenging to invert for it. So that's why seismologists prefer to apply crustal corrections, making two big assumptions. One of them is that they assume that they can compute the crustal phase using first-order approximations. And the second biggest assumption is that they assume that they know the crust. However, crustal structure can be highly nonlinear because of the rapid variations in the crustal thickness, which can be 7 kilometers underneath oceans and can be up to 70 kilometers underneath continents such as underneath Himalayas or Andes, which makes crust behave quite nonlinear. and makes the crustal corrections questionable. So here you see a collection of different mantle models, upper mantle models from different groups. And actually these models are showing the radial anisotropy in the upper mantle from 100 kilometers down to 600 kilometers. I'm not going to go into details. What I would like to highlight here is that if you compare, just visually compare these different radially anisotropic models to each other, you can already see significant differences between them. So, which may be actually part of the reason, among many other reasons related to the challenges related to the inverse theory, might be because of the crust. So that's why crust must be addressed properly in inversions. But the same may also be applied to mantle corrections or needs further investigation, especially for the purpose of our study, where mantle corrections are commonly applied to illuminate the core structure. So that needs still to be evaluated. So now I'm going to give a brief introduction to commonly used numerical methods in seismology. So the computation of seismograms forms the forward problem of seismology. So the goal is to solve the equation of motion numerically, where S is the displacement vector in 3 components, rho is the density, and here you see T is the stress tensor, and F is the seismic source that generates the wave motion. And in our case, it doesn't have to be, but in our case, the seismic source is an earthquake source described by a moment tensor and the source time function S. And using Hooke's law, we can define the relation between the stress tensor and the strain tensor through a 4th order elastic tensor. And to solve the partial differential equation, we need to define then the boundary conditions and the initial conditions, which at the scale of globe, boundary conditions are the free surface conditions where the traction goes to 0 at the free surface, and the initial conditions suggest that the displacement and the velocity is 0 at time 0. Then we can solve this equation of motion using either a strong or a weak method. So in the strong formulation, we are trying to solve the equation of motion in the differential form. And it's also common to reformulate this differential form in terms of displacement into velocity stress formulation, just because to increase the numerical accuracy in simulations. It's easier to deal with first order derivatives. And an example for the strong methods is the finite difference method. Or alternatively, the equation of motion can be solved in the weak form, which is the integral form. It doesn't mean that it's weaker than strong forms. It just refers to the integral form of the equation of motion, where both sides of the equation of motion is dotted with a test vector W and integrated over a volume. And here we just replace the source term with our earthquake source, which can be either a point source or it can be a finite source. And for details of these weak and strong methods, which are commonly used in seismology, I refer everyone to have a look at the Computation Seismology book by Heiner Igel, which is a great book to summarize or have an introduction to the numerical methods in seismology. So the weak methods, some of the examples for weak methods, or the most famous ones, are the finite elements and spectral elements methods, which implicitly accounts for free surface boundary condition. Fluid-solid coupling terms may be explicitly added. Source term explicitly integrated in the formulation, and the weak formulation is valid for any test vector. So I would like to emphasize that there is not a single numerical method that is superior than the others in terms of the accuracy or the efficiency of computation numerical simulations. So the users must choose a numerical method according to the problem they have at their hands. But at the scale of globe, to this end, the spectral element method stands out to be the most successful to simulate the global wave propagation, mainly because of the spatial basis function that are being used, Gauss-Lobato-Legendre polynomials, which leads to a diagonal mass matrix that makes parallel implementation very efficient and then makes these global wave simulations feasible. So spectral element method is a higher order finite element method. So it has the accuracy of pseudo-spectral element methods with the flexibility of finite element methods in terms of meshing the spatial domain. And the mesh can honor the major discontinuities, and an explicit time marching scheme is being used. So here are a couple of references that the people or seismologists may like to have a look at for further information. So one of the critical aspects of these numerical simulations is the implementation of crust, because as I already mentioned, crust has such a strong influence on seismic waveforms, and also it has the simulation of the wave propagation in the crust is kind of the most expensive part of the global simulations because of the shorter wavelengths. It's pretty crucial for the accuracy of simulations and the success of full waveform inversions. So, for instance, this is an example of implementation of crust in one of the spectral element wave propagation solver SpecTime 3D globe, where MOHO is honored if the crustal thickness is less than 15 kilometers or larger than 35 kilometers. Mainly to increase the sampling of the oceanic crust with one spectral element, and where the continental crust is represented by two spectral elements. But any crustal thickness between 15 to 35 kilometers, which are denoted by the white areas, which are the transition between the oceans and continents, the crust is not strictly honored. But the mesh just runs through the grid points of the numerical simulations. This is one way of increasing the accuracy or the implementation of crust in numerical methods. Or another approach is homogenization, where rather than using a classical mesh, the crustal model is replaced by its long wavelength equivalent, which ultimately gives the same response. And this is mainly advantageous to speed up the simulations and also make it easier for some cases to deal with crustal complexities. So this is an example of numerical wave simulations at the global scale, but from another planet, Mars. So basically, you are looking at seismic wave propagation on Mars, where topography, crustal thickness variations, rotation, ellipticity, gravity, and attenuation of the planet have taken into account. So if I just start the movie again and just stop here, so here you see the body waves, and these are the surface waves that just passed through, for instance, one of the largest crater on Mars, Hellas Planitia, where we have the thinnest crustal thickness. where you can see how surface waves are speeding up and how the wavefront of surface waves have been distorted by the topography of Mars and the 3D crustal variations on Mars. So the same simulations are now routinely made for the Earth, and they are also used in imaging using the adjoint method. So once you have the numerical simulations of the seismograms, then the question is, how can we incorporate those 3D wave simulations in seismic tomography? So this is going to be a nonlinear inverse problem, but what is being done in seismic imaging is that assume that you have a set of initial model parameters denoted by m, and if you perturb it a bit by delta m, and define a misfit function, a metric between the observed and synthetic data, which can be L2 norm waveform difference or travel time or amplitude differences, etc. Anything, any misfit function of your choice. And then expand your misfit function with the model parameters, perturbed model parameters into Taylor series. You can readily see that the first order derivative of the misfit function gives you the gradient of your misfit function, whereas the second order derivatives with respect to model parameters gives you the Hessian. And if you have access to both the Hessian and the gradient of your misfit function, then you can optimize your inverse problem using a Gauss-Newton method. However, with numerical methods, it's not possible because of the size and the computational output to store the entire global wave field. It's not possible right now to compute the Hessian, but we can compute the gradients. But then what can we do if we don't have access to Hessian? So this is actually the basis of the adjoint methods, how the models can be updated just by using the gradient of a misfit function. So assume that you have a misfit function like this. This is the L2 norm waveform difference between the synthetics and the observed data. And as I said, you can choose any misfit function that you like, but the choice of misfit function can be very critical for the success of the adjoint inversions. But maybe that might be better to have a separate lecture on the measurements. But here, let's choose the simplest, well-known and well-applied waveform misfit. And the misfit function where its gradient can be given like this, which is based on the difference between the synthetics and observed data multiplied by the perturbations in the displacement wave field. And where we can write the perturbations in displacement in terms of Born approximation, where we have the perturbations in density, this is the Green's function. And here we have the second time derivative of displacement, which is the acceleration. And here we have the perturbations in the elastic tensor and the spatial derivatives of the Green's function and the displacement wave field. So if we use the reciprocity of the Green's function and then reverse the time, we can see that we can rewrite a second wave field, which is going to be called adjoint wave field, which depends on the Green's function and the difference between the synthetic and observed data integrated over volume and time. And this wave field is basically generated by your misfit function. And that is going to be called as the adjoint source, which generates the second adjoint wave field. And here is the mathematical expression of how then the gradient can be computed. So if you define your gradient in terms of model parameters, this is the kernel density kernel and with the density perturbations, and this is the kernel of the elastic tensor with the perturbations in elastic tensor, where the goal is to compute these kernels. So if you look at the mathematical expression for the density kernel, for instance, you have the density and two wave fields are dotted with each other. The acceleration, the forward acceleration is dotted with the adjoint wave field. So basically that means you need two numerical simulations to be able to compute your sensitivity kernels or the Fresnel kernels. One for the forward wave field and the other one is for the adjoint wave field. So for those who would prefer some visual explanation, this is what it's all about. So assume that you have a seismic source injected at a location denoted by star here, and you are going to record the seismic wave propagation at a station located here denoted by square. So as the time progresses, you see the seismic waves are being propagated. Here you see the S wave, and then here you see the reflected S wave from the free surface. And after a certain time, your station is recording S and SS waves. So once you have these simulation results, and then make comparisons to observed data, and make some measurements on them, and then compute the adjoint source, like this, which is, in the case of cross-correlation travel times, it's just the time derivative of your waveforms. And then inject these adjoint source, this time at the location of your station, and then run simulations, but this time backward in time. Again, you see that seismic waves are propagating, but this time backward in time, and then they are going to be recorded at the location of your original seismic source. So these two simulations are exactly the same because you are using the same Green's function and you are taking advantage of the reciprocity of the Green's function. But the only thing that is different between these two simulations is the source term, which is the regular seismic source in the regular wave field, and which is an adjoint source based on the difference between your observed and synthetic data. And then if you look at their correlation and then integrate it over time, you then get these Fresnel kernels for any specific seismic phase. And this is your, basically, this is nothing else but the gradient of your misfit function if you then compute these for all the observables and from all data and simply sum them up. So if you compute these sensitivity kernels now in 3D, let's say for a well-isolated P wave, then you get these classical banana donut kernels. And the shape or the width of these kernels directly depend on the period band, the minimum period of your seismic waveforms. For instance, here you see 3 examples from 9 seconds to 18 and 27 seconds with minimum periods. And as you see, as the period increases, the width of the data sensitivities or the Fresnel kernels increase. And as you decrease the period, you start having narrower banana donuts, and which then collapse onto ray path in the high frequency limit, which is the ray approximation. And the beauty of the numerical methods is that then you don't need to worry about which wiggle you are dealing with. And you can basically compute these data sensitivities. In other words, how your data is affected by the Earth structure. You can do this for any wiggle in your seismogram. So here you see a comparison between S waves and core reflections, SCS phases. And this is another example for surface waves. This is what you would see if you look from the top, and this is how the surface wave sensitivity of the Rayleigh waves would look like on a cross section. And as I said, you can just use these powerful tools to understand what every wiggle means in your seismograms. This is an example from upper mantle discontinuities, seismic phase, the precursor sensitive to the upper mantle discontinuities. The first kernel shows a beautiful S-diffracted wave, and then the B and D, they are actually the sensitivities of the 420 and 660 discontinuity SS precursors. But you see that actually what you select here is the precursors, which look very plain and simple. However, when you compute their sensitivities, you see that their sensitivities are not just the SS phases that are reflected from the upper mantle discontinuities, but there are some more complicated things are going on, or there are actually multiple arrivals within the same time window, which cannot be modeled or captured by ray theoretical approximation. And here, this is a beautiful SS reflection, S reflection from the free surface. So once we compute the gradient numerically for any observable or for any 3D background models, then how can we update the seismic models using these computed gradients? Just remember that in this case, we don't have access to Hessian. That's why we cannot use Gauss-Newton methods. But we can use some gradient-based optimization techniques. So the most famous ones are the steepest descent, conjugate gradient, or LBFGS, limited memory BFGS methods. So how it works is that, first of all, you choose again a misfit function and then compute the misfit between your observed and synthetic waveforms. And then you just calculate the gradient of your misfit function. In this case, you compute it numerically using these numerical methods and simulations. And then this computed gradient, the minus of the computed gradient for the starting model, gives you the search direction. Once you know in which direction you should be updating your model, you then need to decide how much you should be perturbing your model. Then you need to perform a line search, calculating your misfit again for different test models, differently perturbed test models, and then choosing the model which gives you the minimum misfit. And then update your model in the search direction and with the perturbed model that gives you the minimum misfit at the line search. And then you just calculate once you update your model, you again recalculate the gradient, and then you continue this process iteratively. But in the next iterations, instead of using steepest descent, which is simply the minus of the gradient itself, you can use more sophisticated and methods such as conjugate gradient or LBFGS, basically, which use more information from the gradients from the previous iterations as well. So conjugate gradient just makes use of the gradient information from the previous iteration, not only the current gradient, so which helps speed up the convergence. And in the LBFGS sense, you basically try to estimate the Hessian kernel using the gradients from multiple iterations. So then if you are happy with the misfit difference, or if your algorithm converges, then you can get your desired model and stop the iterative process. So this is basically the summary of this adjoint tomography workflow. First of all, you select your database, like an earthquakes, and you request the data, observed data, and then you compute the synthetic seismograms correspond to these observed data. Then you have n observed data and n synthetic data, and then you compare them to each other, you process them, select measurement windows, then make measurements, and then compute adjoint sources. And this part is the pre-processing part of the adjoint workflow. And once you have the adjoint sources, you can run the adjoint simulations, which are numerical. And then you have the event kernels, which are the sensitivity kernels computed for each event. And then you just sum up those event kernels and get the total gradient. And then you process your gradient a bit. You precondition and smooth the gradient, and then determine the step length through line search, and then update your model. And this part is the post-processing part. So the adjoint tomography workflow has three major steps: pre-processing part, post-processing part, and the numerical simulations part. And the numerical simulations, the forward and the adjoint simulations, are the most expensive part of the full waveform inversion, or the adjoint inversions. So this process just continues until convergence. So here, just for fun, I want to give some background information about the history of the full waveform inversion and the global seismic models. So the first global seismic models came out in 1984 from Harvard group and the Caltech group. And actually in 1987, we had the first colorful images of the Earth's mantle. And somehow this 1984 was such a successful year. And another independent seismologist, but this time from exploration side, exploration seismology, Albert Tarantova, wrote a theoretical paper where basically he gave the recipe of these adjoint inversions. And in his abstract, he already mentioned how the full waveform inversion should be performed. He says each step of the iterative algorithm essentially consists of a forward propagation of the actual sources in the current model, and the forward propagation, this time backward in time, of the data residuals. This is the recipe of adjoint methods. And then 2 years later, in 1986, this theory is applied in a 2D problem to image such a 2D cylindrical body. And then they perform 5 iterations on the supercomputer of that time from Total. And then they concluded that the main limitation of numerical methods is their computational cost in both time and memory requirements. So actually, that's the reason why we had to wait more than 30 years to use these techniques at the scale of globe. And so now we can, using these techniques, we can image the Earth's interior at the global scale by computing forward simulations and data sensitivity kernels in 3D background models using spectral-element and adjoint methods. Crust and mantle are inverted simultaneously, so no crustal corrections are used, and hopefully for the outer core, we don't need to use mantle corrections either. This is what we are going to investigate, and these are the first generation global adjoint tomography models. This is just a comparison between what was done in 86 and 2016 in the first global adjoint tomography models. Just a comparison of the size. In their case, the study region was like 1 by 1 kilometer by 1 kilometer, and in this case, this is the entire globe. They had 200 by 200 grid points, and in the current resolution, down to 17 seconds, the global adjoint tomography models have more than 300 million grid points. They used 8 shots, 400 receivers. In the first model, 253 earthquakes was used. Each earthquake was recorded by about 1,000 stations. It was a 2D acoustic problem, and at the global scale, we have to deal with 3D inelastic simulations. It was the duration of seismograms was 8 seconds, and now we are computing routinely 180-minute seismograms to also capture major earthquakes. And in the second generation model, actually data from 1480 earthquakes was used. So what is next? Actually, after the implementation of these adjoint techniques to image the Earth's mantle at the global scale, now the next step for us is to start investigating the Earth's uppermost outer core using these beautiful SmKS phases. So here you see some initially computed sensitivity kernels for SKKS and SKKKS phases using PREM model and the 3D mantle S40RTS together with 3D crustal model crust 2.0. So you can see the change in the sensitivities, especially in the outer core, how you can see for the SKKS phase, how the sensitivity of the wave propagation within the outer core is changing, although the outer core part, the model is the same in both simulations. So actually this change in the kernels is mainly coming from the mantle. And you can see a bit more changes for SKKKS, or the effect of mantle heterogeneities on the outer core part of simulations. And our goal is to now to check how the mantle heterogeneities are affecting the wave propagation or the sensitivities of these phases in the outer core, and how can we further improve the resolution of the outer core models. And I'm giving you a spoiler and an advertisement of the next talk by Mila in 2 weeks to learn more about shear wave splitting and SmKS phases with 3D wave simulations. So as a summary, numerical simulations allow us to capture the full physics in wave simulations. We can avoid approximations and corrections in seismic imaging. And we can use every wiggle in seismic tomography, which dramatically increases the amount of information that goes into seismic images. And next, we have to also take the full physics into account in the inverse problem by using some better parameterizations such as azimuthal anisotropy or body wave anisotropy and elasticity source parameters, and addressing internal topographies as well. And we can now use these numerical simulations to investigate Earth's interior at all scales with 3D simulations. And within this project, our goal is to investigate the outer core with 3D simulations. So we will investigate the following problems: the effect of mantle corrections on outer core measurements, integrate 3D wave simulations into array measurements. We will assess the newly constructed outer core models using 3D wave simulations. And our ultimate goal is to go towards full waveform inversion of the outer core, which is going to be pretty challenging, mainly because of the trade-off between the mantle structure and anisotropy and the outer core structure. But our goal is to investigate and to come up with a framework to better image the Earth's outer core. Thank you.